Okay, hello everyone. This is actually our first live class in weeks, so I hope you are doing good. It has been several very crazy weeks. Thank you for being here today. So this slide shows the statistics of the midterm. The highest score we have is 90. The lowest is 25. Average is 65. Median is 70. 3 out of 13 had 80 or higher. 7 out of 13 had 70 or higher. So I consider um, more than half of the class did a good job there. 10 out of 13 had 60 or higher. So for those who didn't do very well in the midterm, I would say the key is to understand what we did, all the examples we went through in the class, get your hands dirty, uh, just to try them. It's not only just watching videos, but also do that when you try to write the exploit, you will find out what are the problems and also the homework. So make sure you understand all the exploits, and not only you understand those, but you should be able to craft those exploits without any help. Also, um, so the midterm is only 100 points anyway. So two homework is like 90 points, and sometimes I give you extra. And also for the final, I will try to provide some hints and give you guys more time because during the midterm, one thing is I intentionally didn't give you any hints, and there are 4 challenges, and you need to find out which one is easier, which one is harder, and then decide which one to crack first. So for the final, probably I will um, change it a little bit. I will give different points for different questions, and the harder ones will weigh a little bit more, so you can tell which one. At least from what I say, I think those ones are relatively easier. Okay, so for the final, probably we will have more time. So I hope you can crack the program in time. As long as so, my philosophy is as long as you can do it, I don't really mind give you a little bit longer time to do that. Okay. So at this point, you don't need to worry about the final grade. As long as you do your homework well, I think you can still get a very good grades. And also, this is a graduate level class, so I have much more flexibility to curve it. So I do not say. I think most of you are doing well, so I don't worry too much. Okay. Also, I have an announcement to make. Next semester, I will offer another class, but it will be a seminar class. It's 700. That class will be on advanced software security. I call it advanced software security techniques and tools. So this semester, what we have been doing is to learn all kinds of vulnerability types. We also try to understand precisely what is going on with each program, each vulnerability, each exploit. I use the word precisely, right? Every time we try to understand every byte there, okay? So that's because this is manual analysis. I really want you to understand everything. But next semester, the class, it will be more automatic analysis. So with the background you have in this class, we will learn how to use all kinds of static and dynamic analysis tools and approaches to automatically find vulnerabilities at different levels, at a source code level, bytecode level, and the binary code level. We probably will not do much about bytecode level. So there are a lot of systems use bytecode, but personally, I haven't done much with bytecode. I did some Android before, but I don't really enjoy Android that much. Um, so we were even think about how to generate exploits automatically. So if we're talking about doing things automatically, you can imagine there will be a lot of reasoning, automatic reasoning. There will be a lot of guessing involved. So sometimes as the people who developed those automatic tools that generate exploits, you don't really precisely understand each part. Sometimes it's a black box to you. You don't know the target that well, but still you should be able to crack it. Also, we will cover some basic techniques, including program analysis, dynamic programming instrumentation, symbolic execution, fuzzing, set tools. So we're going to use those tools. However, this class will be a seminar class, so which means some of you can take it as a 1 credit class, some of you can take it 2 credit, and even 3 credits. So if you take this as a 3 credit class, you will do a course project aiming at publish a paper, and also you will do all the labs. If you are only taking it as a 1 credit, I think right now I'm still debating here. Maybe you only needed to do the paper presentation and also the lectures, so you don't have to do all the labs. Okay, so the workload will differ. So this is one advertisement. I hope you enjoy this semester class, and we'll keep learning what we're doing here. So you can take a next semester class as well. Okay, so today the agenda is very simple. We will just do format string vulnerability. So how many of you actually finished the video last class? Okay, good. Okay, so format string is the one I consider quite confusing. If you don't do it, it's quite confusing. Yeah. So let's see what we have here. So this is actually the program we looked at last class. There are two local variables, buff1 and buff2, each has 100 bytes, at least at state level. The program reads from std_in, reads 99 bytes. So actually fgets were added 2 bytes there, so I should put this 98, but that really matter that much. So it will read 99 bytes into buff2, and buff2 will be used as the format string here to print out another string into buff1. And even though buff2 can only be shorter than 100 bytes, but it will be used as it itself can be used as a format string. So you can use something like %1000D or %1000U to expand that specifier into something huge. So buff1 will actually there can be a buffer overflow that overwrite everything above buff1, including the return address and everything. So this is the code we used. This is a program we used last week to do the buffer overflow, and we used share codes there to inject the share code and eventually give it control to the share code. So today we actually only have one example, but we're going to do multiple attacks on this program. So if you haven't downloaded the program yet, oh, hold on. This is not the one we're using. Actually, this one is a little bit harder, so I plan to give this one as your homework. So the code we're using is actually this one, FS5. If you haven't downloaded it, download it from my website. Did I put them? Can someone tell me if I put the right one there? I'm supposed
it's
to.
It's W10, Dr. Zhou.
It's what?
W10, was that the one you wanted?
Yes, yes.
Okay. I just dropped it in the chat.
Yeah, supposed to be format string, format S5. Yeah. Is that correct one, or did I put FS4 there?
I unzipped it. It looks good.
Okay, cool. So this is a program. This is a program we're going to use today, and we are going to hack it in several different ways. Let's see, make file here. So this one is to make things a little bit easier. I used no PIE here. I actually put the no stack protector here, but I don't think it matters. Well, even with stack protector, this one should work because we're not trying to put share code on the stack. So if you look at the source code here, this is our source code. We have a main function which calls the valve function. After valve returns, we can print the secret if the global variable auth is not 0. So the global variable auth is initialized to 0. By the way, all the uninitialized global variable auth were also be set to 0 as the C standard required. And the print secret function will just print a string and just exit. The vulnerable function is the same as the function we had in FS2, I think. So we have a buffer, 120 bytes. Then we're going to read 100 and at most 118 bytes for stdin. So fgets and 2 more characters there. So it will not overwrite the temp buffer. Then there is a vulnerable printf, which use your input as the format string. So your goal here is to first override the auth. That's our first goal, to override auth. So the program will print out a print secret. The second goal is to override the return address on the stack. So maybe the valve return address on the stack, then we can directly jump to print secret. Obviously, if you can do that, you can easily make a return to libc call, right? You can, instead of jumping to print to secret, you can jump to the system function in the C library, find a string being SL, then you should be able to get a share there. However, this one, we cannot directly buffer overflow this. So we are going to use a new trick we actually talked last week, but we haven't used it. So the trick is %n. So %n, like I said, before I learned buffer format string vulnerability, I didn't even know there exists this %n. As a C programmer, how many of you use this one? I never used it as a C programmer, right? So I only use this for hacking. So what %n does is to write how many characters has been printed out by this function call, and write that to an integer. And that integer can be anywhere, can be global, can be local, as long as you give the address to that integer. So you can basically write anything to anywhere using this feature. Of course, it's a little bit more complicated, but you get the feeling that as long as you specify an address to it, you can write anything to anywhere in that memory space. Also, there are some other length flags can help us. Like the HH1 is basically half-half. So half-half of 4 bytes in this case is 1 byte. Then, or you can have H, it's 2 bytes. So this can guarantee that you are not writing 4 bytes. Instead, you are writing 1 byte or 2 bytes to sometimes make things much more convenient for you. So our goal is to override the auth to execute the print secret, and also override the return address. Doesn't have to be the valve return address. Any return address or any function pointer, any code pointer on the stack, or even any other places to execute print secret. So let's see, where do we start? So this one I will actually use the I use the node PIE, so you can say that use NM, we can find out where this global variable is. So the global variable is at this hard-coded address. It's determined by either the compile time, and you also say that the auth, this global variable is initialized to 0. We initialized in our source code, but it's not in the data section. This variable is still in the BSS section, which is uninitialized. The reason is everything in the uninitialized section will be initialized to 0. So compiler just decide to put this in the uninitialized section. So the loader will initialize it to 0 instead of the compiler need to generate some code to initialize to 0. So this one is not really in data section, but in BSS section. Well, I mean, for hacking purposes, this doesn't really matter for us. So this is the auth variable. Then you guys watched the video of last week. How do you guys want to approach this? So what we can do is, so this program where, oh, it will take from std_in. So what we can do, so let's try to just try to print several %x here and say what we get. If we just put this to quick exploit, then we run this program, redirect to this one, then the program will read those and print out some values on the stack, right? So this is a trick we used last week to either view the stack or pop things from the stack. So basically, we're popping out things from the stack, moving the ESP. Another trick we used last week is to put some address at the beginning of this. Remember? We put an address at the beginning of this. Then we put a lot of %x there, and eventually the ESP will point to that address. Okay. The trick here is you always want to put the address. Well, technically, you can put the address anywhere in that string. It doesn't have to be at the beginning, right? You can put it at the end, you can put it in the middle, you can put it in the beginning. Eventually, you can somehow manipulate that ESP to point to your string. But the problem is if you put it at the end of this and you add another %x or anything there, that address change. So it's not very convenient for you. You need to do more careful calculation to actually point to your string. So that's why usually we just put it at the beginning. But like I said, a lot of hacking is kind of like art. So there are so many different ways to do art anyway. But we try to choose the easier way. So what we're trying to do, we're trying to overwrite the auth global variable. And we have its address here. So it will be 28 C0 C0 0 0 4 0 8 0 4 0 8. Okay, so now next we are trying to find out how many pops we need to do to point our ESP to this string. So we just do this, then we do this. We can say right now it first print out this thing, and a lot of those 4 characters, some of them are not really readable or printable. So that's why we only have say one here. Then we'll print out 7 6 and 3. So here, this is a stack. We do not see our string there. Makes this a little bit more clear. And to underscore here, then we start popping more things. So hopefully at some point we can find this string on the stack, this string itself on the stack. So we do it again. What do we have here? Do you find that address? So this is our address. You see that? 8 60804 C028. That is our address of the OS. That is what we put at the beginning of that string. Of course, to make things look a little better, we can do this. So we make sure everything is 8 characters. Oh, this is actually important for later exploit, because we need to know how many bytes we have been, how many characters we have been printing out. So if we do this, we can say everything begin, that's the string. Then we print out 76, this one, and this is clearly, oh no, this one is not our address. This is something else. I'm not sure what this is. It looks like so 921B. Looks like code 921B. So you can say 91 here is text. So I guess 92 is also text. So this one looks like a return address, probably main function. No, not main function. Oh, yeah, looks like main function. So main function is 9254, right? So 921B is above that. So maybe this is a return address. The Valfu's return address on from the main function. After that, we have 0, we have 1. So this one probably looks like a saved EBP here. Looks like a stack. So those two, because the Valfu doesn't have any, does it have any? So this one does have some global variables. Oh, so this one not necessarily is main's address. It probably could be Valfu's address. So where is Valfu? Oh yeah, so Valfu is high, like a lower address. So this is main. Okay. Oh yeah, this is actually Valfu. So this is actually inside the printf function. In printf, it has a saved EBP of the Valfu. That's the saved EBP of Valfu. Then this one is the return address in Valfu. So you can see here Valfu is 9208. So very close to this one. This is just 921B. So this function doesn't really, so printf is only taking one argument here. So I'm not sure what's those two, could be some local variables. Then we have our string. This is our string. What do we put it? So let's say how many we need to pop out before we find our string. So this is 1. This is 1%x, 2, 3, 4, 5, 6. So basically, we need to use 5%x here. So this is 1, 2, 3, 4, 5. So if we do this, we should not be able to print out our current. Should not print out our string. But however, after we do this, our pointer, the ESP, will point to this string. So now we just need to change our exploit a little bit by adding a %n here. So now the %n will go to the stack to find an address, which we put there is this address. And the %n will write how many bytes we have been writing so far to that address. So how many bytes we have been writing so far? We can actually calculate. So this is 1 byte, 2 byte, 3 byte, 4 byte, 5, 6. So here is 6 bytes. Then for each of %x, it's 8 bytes, 8 characters. 1, 2, 3, 4, 5. So it was 40. So it's 46. So we are actually writing 46. So after we do this, the auth global variable is supposed to be 46, and we should be able to print out the secret. So we didn't really print out the value of it, but we can debug to find out if that's 46. Does that make sense to you? So this one is actually quite easy, but let's still do a debug this one. We can do a full here, run this one. We can exploit. Now we're running the in Rufu, so I should be able to exploit, right? So this value is 0. So we keep doing. After that printf, we should be overwrite it. So this is fgets. So this is we input our format string, then the printf will actually use our format string. So after that, we do another print. So we have 62, which 62 in hex, which is 64. 32 in hex, which is 64 in decimal. So that's exactly what we were expecting. So this is how we can overwrite any global variable or local variable here. So how can we use this? How can we use this? Imagine this one. There are so many ways. For example, there is a stack cookies, and somehow we find out what is a stack cookies. Then we can do a buffer overflow first, let's say, or then we can write the stack cookies, then jump to the code. Or there are other secrets we can write in the memory space. We just can use this approach to overwrite. And one challenge we have here is the number we want to overwrite. It's actually quite small. Here we are overwriting only, the number we overwrite to us is only 64. What if we want to overwrite something super big, for example, like an address? For example, an address of the stack start with FF. That's a huge thing, right? That could be very tricky using this approach. Let's just try that. This is what we want to do. Okay. Let's say here, instead of print out the last one with 8 characters, we printed out it was a huge number. Okay. So technically, this is a huge number. Technically, if this is successful, then that global variable auth will change to that huge number plus some small numbers, right? So we can change it. So in theory, we can change this to arbitrary number. We can override arbitrary number we want. But if we really run this, you can say the problem is it takes forever because it's actually printing out those characters, right? So here we only print out 8 characters. So it's very fast. We're printing out 8 characters. Here we're printing out a huge character. And that literally could take forever, like millions of years, because the number is so huge, right? So this approach doesn't really work if you want to overwrite any value to any address. If the value is too big, this approach doesn't really work. The program will just hang there forever. But this is a problem we have been handling for a while. Like when we tackle the stack canaries, the stack cookies, how do we do it? Even instead of writing 4 bytes at the same time, we can write 1 byte each time. Or we overwrite 4 bytes, but we only use the least significant byte. So still we're like writing 1 byte. We don't care about the other 3. We make them small. Then we move our pointer a little bit to write the next 3 bytes, 1 by 1. So that's how we solve the problem. So this is what we are going to do with our second challenge. So our second challenge here is to override the return address and execute print secret. So we are, so what kind of information we need here? We First of all, we need the address of print secret. In this case is this. Let me copy this, put it down somewhere. So this is location we want to jump to 0804 91D6. This is the location we want to jump to. And we are going to overwrite the return address of the Vulnerability function. So we need to find out where is the return address on the Vulnerability function. For that, we can cheat a little bit with GDB here. So we set a breakpoint on Vulnerability, just to run it. Now we are in Vulnerability. Then just by printing out the ESP, we can get the address. So this is the address. This is where the return address of in the main function stored on the stack of Vulnerability. So we can examine that. Examine that address. So you can see this is the address from 926F. So if we do this symbol of the main function, you can see the 926F is in the main function. It's the instruction after we call Vulnerability. So that's the return address on the Vulnerability stack. And so let's store. Do we need to store this address? No, we only need this address. So this is where it is stored. So what it is? This one is return address is at this location, and our target is at this address. Any question there? And also for this one, we're lucky because everything is because we're not doing a return libc here. We're only doing return to another function. As you can see, the first 2 bytes are the same anyway. The first 2 bytes are always 0804. So to override this return address, we only need to override 2 bytes. We don't need to override 4 bytes. However, you will say, sure, even overwriting that 2 bytes can be really, really confusing. Okay, so where are we? We have those 2 addresses. Now we can get out. Now we have our. This was our exploit to overwrite. This was our exploit to overwrite auth. Now we are not writing auth anymore. We're overwriting that return address. So we change this part. After we change this, we still have 5 of those %x, and that guarantees us after popping, we point to this address. So the one we are going to overwrite is what? 8C D0 FF. Do we need those 2? Yeah, it's better we don't have those. I'm sure you. I will show you later why. Okay, I remove those 2 underscores, and later I will actually remove the dot because it will make our. So basically here, every time the %08x will pop, will print out 8 bytes, 8 characters. But there is another dot here, will print another byte out. And that will make our hacking very difficult because every time we add there will be 1 byte off. So we will remove that later. Okay, now, so let's do this. Okay, so what is this code going to do? This exploit is not going to, because we didn't use %n here, so it's not supposed to print out anything. So we just check if the pointer is good. ESP is pointing to our address. So what we can do here is we have a %n here, then we will be able to overwrite that the return address on stack. However, we're not overwriting it to the value we want. We're basically overwriting to something like 1, 2, 3, 4. This is 4 bytes and plus something like 48 or something like that. And that is obviously not a valid address. So that's why if we do a cat exploit, type this into to make sure the stack is consistent. So we do this. This should give us a segment fault. Yeah, so it triggers segment fault. The reason it triggers segment fault is because we override the return address. We can actually debug this to confirm this. So now we say set a breakpoint at awful. What? No single table. Oh, sorry. Which one? Should be this one first. Then GDB this. Then let's say awful. Then we're going to run this with exploit. So now we are at our walkthrough. So we're at the beginning, so we can check ESP. It's print out. ESP points to the address we recorded there. If we examine EXP, we get what is stored on the stack. This is our return address. This is a valid return address. So if we keep running until this printf, we keep running. Now we are at this printf. Okay, so we can. How do we examine the return address now? Remember, how do we examine the return address? Should we do XX ESP? No, right? Because ESP right now doesn't point to the return address anymore. Only at the very beginning of the program, the ESP points to the return address. So what do we do? Everyone forgot.
XX EBP plus 4.
Exactly. So we can do EBP plus 4. So right now it's still valid. Okay, we haven't overwrite this. Now we call printf, which is vulnerable. Then we examine this again. You can see this one is overwritten to the number of characters. The printf has written so far, which in this case is 48 bytes. Okay. So obviously, then when we do the return here, it will return to an invalid code address. So it's invalid address actually, not only the code. So if we keep doing this, let's say now we are at here, 3 more instructions, 253. So now we are here. The next, so when we do the return, it will return that to that invalid address. That's where we get a segment fault. Well, technically, right now we're still, let's do it again. Now we get a segment fault. This one doesn't trigger segment fault because that's the next instruction to do. So we haven't do anything with it. Okay. So going back, but you can see that this is how we can overwrite that return address. The next thing we want to do is we want to overwrite that return address to the value we want. What is the value again? That value is a huge number. Okay. So one approach we can use, which doesn't work, is we put that huge value there. What is that? 80491 D6. This is the address of the print secret. So you can see it's a big number. Um, if we just use this number here, let's say instead of using 8, we just do this, right? So technically, if your computer runs fast enough, this should generate an exploit that works. However, no computer is that fast. It takes forever. See? So right now what's doing? It's just printing out things. And there are how many? Millions? No more than millions. Hundreds, millions of them. Oh, actually this one printed out very fast. But did it work? It doesn't work because I didn't give it the correct one. Because we're also printing out other things. There are other things. So if we manipulate with this one, it may work. But this number is not that big, right? Because the first one is 0. So the number is not that big. If the first character is F, it's a huge number. So this approach, even if it may work in this example, it's not generic enough. So what we're going to do is using a more generic approach to make this work. So how do we use this? How do we do this? We're going to use those tricks. We're going to override 1 byte instead of overwriting 4 bytes here. So here we're overwriting 4 bytes. So instead of using %n, we're going to use %HHN. So some systems, the HHN may not work. So some systems you probably can only use HN, you override 2 bytes. Okay. So if we override 1 byte, let's try to overwrite the least significant byte first, which is D6. The target is D6. Then we need to calculate how many we're writing. So here is 1, 2, 3, 4. This one is 8 bytes. Let's remove this dot to make things easier. Okay. Here we have 4 bytes. 1, 2, 3, 4. Then we have 8. No. We have 5 of those %08x. So each of those will be replaced with 8 bytes. So 5 of those will be 40 bytes, including these 4 bytes here. We already, at this point, we already write how many bytes? We already write 44 bytes. Okay, we already write 44 bytes. And the value we want to overwrite is D6. The value we want to overwrite is D6. So if we use D6, by the way, the reason I say D6 is because you know why it's D6, right? That's the that's the address of print secret. So D6 is 240. So that means we need to overwrite 240 minus 44, right? So we still need to overwrite. We still need to print out 170 bytes. And that's easy. We know how to do that. We just use another percentage 170, then we use D. Okay. So this one percentage 170D, we just read the stack. Whatever you read the stack, it will print out it as an integer, which is 170 characters. So at this point, now we have 4 bytes, 40 bytes, 170 bytes together. We have we output 214 bytes. Then we write that 214 to that address which is here. So by this, we are supposed to override the least significant byte. Let's just does that make sense? Does that make sense to you? Let's see if it works. Let's do the symbol value. So where do we want to set a breakpoint? We just want to set a breakpoint before and after the print. Now we can run this program. This is how we run it. We can it with exploit. Okay, so now we Why it's not running? Oh, I set a lot of breakpoint. Okay. Just continue. Now we are here. Exam our stack again. EBP +4. That's the return address. So we're only overriding the last byte here. We override it to D6. That's our plan. So we do one step. There's error. It's not working. Something is wrong here. What's going on? 1, 2, 3, 4, 5. And we'll print out that right. Then we print out another 100 and we print out another 160. Should be good. Why? Any idea what's going on?
This isn't our entire exploit.
No, it's not. We're only trying to override one byte first. The second byte we need to change this a little. Okay.
We're still missing 2 0.8s.
Oh, really?
At the address it's given, so it gives us D014, but look, we're only finding 3 of our 0.8x's, and I believe our exploit has 5 in reality.
Oh, you're talking about here?
Yeah, so this prefix is short.
I think this is only because it's not showing what is at the leading ones.
Yeah, it's the wrong address maybe.
Oh, so you say here we're not pointing to our correct address.
Not the whole exploit.
Yeah, interesting.
But some of it.
Yes, but this is a format. So this is an AP. What's going on here?
So my naive idea is that we extend it a few more bytes and see if we can stretch it to the right length. But
is it because the address I get was not using this one, r.sh? Did I use that one? Let me verify that. So maybe there are several bytes off because of that. So we run this. We print ESP. Right? No, it's correct. D008C, right? So that's our.
Quick question.
Yeah.
Are we accounting for like the first 4, like however many? So if at the exploit string those 8C, it will turn into decimal and it will take 3 bytes.
That would be 4 bytes.
For
4 bytes. Yeah. So even
no, as in when we print them, they will take they will convert to decimal, right? And they will take. So if you go up in your terminal,
okay,
you see they print out as a decimal.
So when you print out, even if it's not printable, even if it's not readable, the printf function still think it print out the character. So that's why it's still 4 bytes.
Okay, so it's just terminal doesn't interpret it correctly.
Exactly. Yeah. You can, for example, you do not print out that to the std out. You print out to a file. It should work, right? You can use the XSD to get that. Yeah. So.
Yeah. Okay. Maybe. Okay. Yeah.
So what's wrong here? The address is 8C D0FFFF. Okay. This looks.
There should be 5%X, right? But we are giving 6.
%X?
Yeah. So if we remove
1, 2, 3, 4. No, 5. We're only doing 5.
And another %D.
Yeah, the D is correct. The D is we want to get the we want to print out something else.
Yeah, but this %D will be the address, right? Because
no, the person.
That I tried with 178D, removing 1% x, and it works.
Oh yeah, you're right. Because this one will add another. This one will print out. This one will actually
Print out
pop
our
something from the stack again, right? Yeah, you're right. So this one will print out things from the stack again. So what we can do is um, we can add maybe
if we remove 1% x and make
you're
it
right.
178D, it works.
Yeah, you're right. So in this case, we need to remove one of those percentage x, and because this one will actually pulp. This one is in terms of pulping, this one is equivalent to percentage 0x. But the number of the characters printed out is different. This one is printing out 170 characters. This one is printing out 8 characters. Okay. So after this, this one will point to the beginning. That's correct. However, because of that, we print out 8. So we are short for 8 characters, right? So that's why we need to add 8 here. For this part, we can debug to figure out. So I think you're right. So now we debug this at just disassemble awful, and yeah. By the way, was that Toad Mother?
Yes.
Okay. So everyone else, you can try to do the same thing when I'm doing this, like what Toma is doing there. Now we set a breakpoint point here. We overwrite this. Yeah, that's exactly the part why I say sometimes the format string is really confusing because everything you are doing there will change the stack. And you need to think what's going on there. So now we have EBP plus 4, which is the correct one. Then we run this. Then this again. And you can say we overwrite this to D6. We overwrite 1 byte. And the D6 is what we want, right? So that's correct calculation. So this one can help us to overwrite 1 byte. However, write over 1 byte is not enough. We need to overwrite 2 bytes here. We also need to change this 92 to 91. And this is quite tricky. If there are 2 printf functions for us to exploit, this will be easy. The first time we overwrite 1 byte. The second time the first time we use a printf to overwrite 1 byte. The second time we use a printf to overwrite another byte. But we don't have 2 printf functions for us to use. We only have 1. So we have to utilize the same printf function to override the second byte as well. Okay. So how do we do this? So first of all, if we want to override the first byte, this is the address. The second byte, we have to use a new address, which is 1 byte higher than this, right? So we need to change this to 8D. We add another 8D, D0, 8D, D0, FF. And because of this, we are printing out 4 more bytes here. We need to think about that. Now we have those. We print out those F, and this one we're pop that, so we'll do this. So far, how many bytes we have written? So we have override D6. What is D6? Not D6 again. So we override a D6 plus 4. So the previous exploit, before we reach percentage , we have a D6. Now we add 4 bytes there. So it's D6 plus 4, which is DA, right? Which is 218. So at this point, when we reach here, we already write 218. So that's why for this number, we need to minus 4. We need to 174 to get the first one right. Then we need the second one, which is HHN. And when we reach here, still we have over 218. But what we want to write is 91. But the value we already have is probably, so the value we have right now is already DA, right? DA is already bigger than 91. But the byte we are going to overwrite is 91. So how do we do that? Any idea how do we do that? What we have already put output, we cannot take it back. So we cannot make it smaller. But still, we only want to get a 91 there. How do we do that? What is the trick we're going to use?
Can we use one edge?
1H? I think, yeah, I think you get what it's doing. So instead of directly writing 191, we're going to write 191, right? This is a byte we're going to overwrite, 191. But because we're only right, so basically we want to output something 191 bytes. So, but this 191 bytes in hex, we'll take 2 bytes, and only 1 byte will be overwritten. So we get 191, we get a 91 zip. So which means we are going, this is a 401 bytes. And here we have, we already have like 218. So which means we are going to do 410, 118. So we need to write another 100 and why it's not giving me that calculator? No, what's the number? I forgot. 218. So we need another 183 bytes there. So what we can do is we put another 183 bytes, right? 183. Yeah, 183. Would this be correct? This is actually not correct, because this one will pop out, because we're using %D, it will pop something from the stack, right? If we pop something from the stack, it will pop the address we want. This is an address. So when the ESP reach here, the ESP actually pointing to, when the string we're passing reach here, the ESP actually points to our address, okay? So if we do %183D here, what we're actually popping out is the address, but we don't want to pop out the address. That's why we just want it to pop out some garbage. Let's say we put 4A there. Then here we need to change this to 0 because we add 4 bytes there. Now we do this. Then when we reach %HHN, we are pointing at our address here. And that is the address we want to write things to. But because of that, here we also need to change a little bit, I think. Let's try this. Let's debug. I would say we do this. Does this make sense? This can be really confusing here, I know. And also my calculation may be wrong. But let's try. when we do this, we do, we just disassemble this. The address we want is this one. We set a breakpoint here. We run our exploit. Okay. Now we are at printf. If we examine the ESP, EBP path 4, we can say nothing is overwritten yet. Now we run this program. One more step. Then we examine the second. We can say, oh, this one is wrong. Our calculation was wrong, but we were able to overwrite this part. And this part is correct. We have D9. This part is wrong. We need 9-1. Instead, we get 8-9. So we are several bytes off. 9-1 minus 8-9 is just 8 bytes. So we are 8 bytes off. So which means we only need to change this to, so this is 179. We just need to change one. This. Okay. So this should be correct. So we can actually just run this without GDB to see if it's correct. We can't exploit. Do this. See, it works. So this one we actually overwrite the last 2 bytes of the return address, and they print out this is a secret. But you can see the calculation here, it's very confusing. And we are only doing the second byte. If you're doing the third byte, you probably need to go back to the first byte to do a lot of calculation. Is everyone doing this right now? So what is everyone's status?
I'm still having a segmentation fault, so I must be missing one small thing.
Okay. So this is actually the one we're going to do. So next, how about someone, I would like to give someone a chance to, so I already show you it works, but on everyone's machine, it will be different. Different address, different everything, right? So anyone want to lead here to share your screen to say how you are doing? Then I will basically give you some advice to anyone.
I can go ahead, Dr. Zhao, since I feel like I'm close at least.
Okay, let me see, where are you here? Oh, yeah, right here. Yeah, now you can share your screen.
Okay, I hope that's visible for everybody.
I can see it, yeah.
So this is what I thought was identical, but I might be missing.
Mm-hmm.
Let's see if I can stretch it to get it one line. Maybe will help too. So the initial address, 4 bytes of garbage.
Mm-hmm.
Second address, I think, is correct. From what
No, you see, the first address and second address should be just 1 byte off. In your case, your second address was the address I was using.
Ah, that's right.
Right.
Okay,
Yeah.
so here it would be system dependent here.
Okay.
Is that the idea?
Maybe just the ED, you know, you have EC there, right?
I see, I
+1,
see.
yeah. So maybe it works.
Okay, then just to wrap up, we have we do a series of 4 8-byte integers, 170, and then half, and then 187 half. Does that seem right?
Mm-hmm. Yeah.
Okay.
Seems good.
That's it.
Oh, you got it. Okay. So that one is easy.
Okay, so the 1 byte separation is what I needed.
Yes, that's the only one you need.
Got
Okay.
it. Okay, I'll
Hey,
turn it over.
I just had a quick question. I think I missed that part, but why do we have 4 bytes of garbage A?
Okay, let me share my screen here.
Yeah, I think it gets popped. Is what we.
Can you see my screen?
Yes.
The reason we have that is we need this percentage D. Well, technically, it doesn't really matter if you use percentage D. You can use percentage U or anything else, right? But you need this to print out more characters, right?
Mm-hmm.
You need to print more characters, so the internal counter in the printf will reach the value you want to reach, right? However, when you do this, the printf will look for something on the stack and pop out. So if you do not put the 4A's garbage here, what will happen is it will print out your address there as a long string 187 or whatever length, right? Then when you reach percentage HHN, the ESP will point to what is after that, which is the percentage 08X. That will not be the valid address you can use to overwrite. Make sense?
So why does it pop? Do we like outs?
That pop is internal, right? Well, that's what we started last class. That's the VA, that's the VA arg function.
Oh, okay.
Right? It will move your ESP to the next argument.
Okay, yeah.
Make sense?
Got it. Yeah.
Okay. Okay. Someone else is close and couldn't solve it. So Phil, if you solved it, you can try to do the return to libc with this one.
Okay, I see.
Yeah. Anyone else wants to lead? She, where are you right now? Yeah, who was talking? Sorry.
I'm Thomas.
Who?
I'm Thomas. Yeah.
Oh, Thomas? Okay, let me find where you are.
Mine, like, it is working on GDB, but outside GDB it's giving.
Oh, that's interesting. Okay, I already make you the co-host, so you can share your screen.
Yeah, you can see my screen.
Yes.
So it's inside GDB.
Yes.
So it's working here. But the same code outside GDB is giving me segmentation.
Okay.
And I checked the value. The value is right. It's 91D6. So here, it's 91D6.
Probably address space randomization, no?
Yeah.
Oh, yes.
Yeah.
Because GDB turns it, yeah.
Yeah, GDB will turn it off. So I have that the command on the slide.
Okay. Yeah, I didn't.
Yeah, try. I think that could be the problem, but let's see if that is really the problem. Yeah. I can send that to you in the chat box. Okay, a minute. Yeah, I send that to you in chat, Zoom chat.
Yeah, I got.
Yeah, most likely that's an issue.
Yeah, it works.
Yeah, that's a problem. So I bet got the problem. Cool. Anyone else have the issue there?
I guess I find another way to change the byte.
Okay, good.
I change
Okay.
the higher bytes and then change the lower byte. Just replace the.
Can you show the screen?
Oh, I don't have. I cannot share my screen.
Oh. Okay. Yeah, you can do it now.
Okay. Okay. Can you see my screen?
Yes.
So this is another way that I try to modify the second byte, and then modifying the last byte. This
Okay.
is another way.
So the idea you have here is you don't. So basically, what we did just now is we use the integer. Basically, we use the integer overflow, right? We use the 1 byte integer overflow. We already write a big number there.
Yeah.
Now we want to write a smaller number. So what do? We overflow that integer and get rid of the most significant byte. So Xi's idea here is we just write the smallest one first.
Yeah.
Then we write the bigger one later. Okay.
Yes. Yeah.
That should work.
It works. Yeah, I already got the secret.
Yeah, but even this approach would not be very generic. It cannot it cannot work for all the problems. For example, let's say. So what I'm trying to say is sometimes you still need to utilize that integer overflow there. It's possible, right? It's possible that, let me see if it's possible. Is there any case you cannot solve? It's a small number there. You probably can solve all the ones, right? Yeah, you probably can solve all the ones, I think. Yeah. Cool. That's very cool. Anyone else wants to share anything? So if you already finished this one, you can start thinking about how to do return to Libc to get a share. So who is Wei here? Wei seems like a new guy. Wei. Okay. Do you know who that is? No? Okay. Don't be shy. I mean, if you're in the class, you can speak. Okay. He's shy or she is shy. Anyway. How about Sharon? Sharon, do you get it?
Yeah.
Okay. Srinikes, do you get it?
Not yet. I actually want to go back and revisit the lecture.
Okay. So you didn't finish last week's lecture?
I finished like 3/4 of it, but then the last one, I think like 20 minutes I didn't do that. Yeah.
Okay. So right now, which part confused you?
I guess just I need to get a better understanding of like the formatting part.
Okay.
So I just need to go watch the lecture again, and I'll ask you if I have any questions.
Okay. How about Jackie? You got it?
Yep, I'm good.
Okay. Gersimran, are you good?
Yeah, similar for me. I need to follow up with the previous lecture.
Okay.
Yeah.
Okay. Then you guys also need to work on the homework of last week. Yeah, this one is a little bit tricky. Charlie, you are good?
They had some kid issues come up partway through the lecture.
Okay.
I'm not even going to go into what that was, but
Okay.
I will, yeah, Oh my goodness. I will re-review and
Okay.
try it again. I got close on it and I picked out what my address is, I think. I just need to look at it again and make sure I'm doing it right.
Okay, cool. How about Sai?
I just have to go through the address part again, Professor, and just review it again. Yeah.
Cool. So you guys, if you are, I would suggest you to working on right now since I'm here, right? So I can help you if the part you don't understand. Also, later after you watch the video again, if you feel you need to talk with me, we can schedule office hour. We haven't met live for much last several weeks, so just shoot me an email. Merwin, are you doing good?
Yeah, I'm doing good. I just had the same issue of the disabling ASLR. So yeah, that was my issue. I'm good now. I'm good.
Okay. I assume you got it?
Well, I had a quick question actually. I want to get back to that 4 A's that we put of garbage.
Yeah.
You said the D, the 170D pops it, right?
Yes.
Like I'm just it pops. I'm just imagining a string, a real string, in a format no vulnerability, just a regular string. When we running fstring without like, let's say I'm just gonna put example like, maybe I could share the chat.
When I say pop it, it's not really accurate. Technically, what happens is some kind of an internal pointer.
Oh, it increments, right? Okay.
Increment, yeah. It's not really pops it, yeah.
So why would it do like a byte past the? Is that because 170D is expected to be there? Oh, wait. Yeah, I see. Like. Okay. Can I share my screen?
Oh, sorry. Now you can share.
Okay. So if I just have this simple printf function, with, let's say, hey, I don't know, today, I don't know, my age is %d, and then we put some integer here, right?
Yes. Yes.
So for instance, this example, I guess does it. So the idea is it puts the int right here, and then it skips those 4 bytes that should be right here. Is that the case, or like?
So in this case, it's not necessarily writing 4 bytes, or let's say 4 characters. It's not necessarily. Here, what you have is only %d. It doesn't specify how many bytes you want it to be, right? So if that integer is very small, it's like, for example, 1 or 0, it will actually be replaced. The %d, the string, will be replaced with 1 character.
But what if okay, I'm gonna split like 10, 12, let's say.
You want to put, yeah. So this one, it guarantees that it will at least be 12 characters. And if that integer is very small, then they will use white space as a padding for that 12 characters. And because we know integer cannot be that big, right? So actually here, it will never be longer than 12 characters. It will only be 12 characters. Make sense?
Yes, but at which point does it like start skipping? Is it like that, moving the pointer by 4 bytes?
So yes. So here's the thing. Let's say if you don't have that int as input.
Okay.
If you don't have this one, so the printf will still look for this integer on the stack, right?
Okay.
But you didn't provide it.
Yeah, so it's gonna be some some address right there.
Exactly, some value on the stack, maybe previous functions, global or local variable, something like that, right? Yeah. Or you you can do percentage, you can do 2 percentage d there and only provide 1 int. That would be the same thing. So you're still missing a arguments there. Yeah.
Okay. Yeah, I'm missing the arguments.
Yes. Well.
Okay. Let's do this.
Yeah. Go ahead.
I'm gonna put like we're gonna put int right here. So
Yes.
just this example.
So the first percentage 12d will look for the argument int you gave there.
Okay.
The second one, percentage 12d, will look for 4 bytes higher than that, which is whatever on the stack. You didn't provide. Yeah.
But okay, it's 4. It's plus 4.
The address is plus 4, but what do you print out? What is the function print out is not plus 4. Yeah.
So let's imagine this is the address on stack. So this is the valid integer. Let's say, I don't know, like full of, I don't know. This is probably not a valid, is it? It's a valid integer, yes, but it's not like it. I will probably just put some random stuff here. Doesn't matter. But in the 4 bytes above that, there's also oops. Oh, this is not a valid.
It doesn't matter. It doesn't matter.
Yeah, it doesn't matter. Yeah. Whatever.
Yeah.
But why does it skip this one to when it puts it here? Why does it skips this value?
It's not really skipping this one. It's actually, okay. What if you put another percentage d there? If you put another percentage d here. So what we're saying is, the third one will be 4 bytes even higher than the second one, right?
That makes sense. Yes.
Yes. So that's what we mean by skip here. The second one we say it's a skipping because we don't care about the value.
But at what point did we okay, I think I missed it, but at what point did we use another %12d afterwards? I don't think we used %12d afterwards.
So here, go back to our exploit. We use that percentage 170d, right?
Oh.
That one we have to use. We have to use that one for printing out 170 characters to the output. And because of that, it will use something on the stack, and it happens to be our address, right?
Okay, no, it makes sense now. Okay, thank you.
Yeah, cool. Good. So how is Ed doing there?
Following along.
Okay. So where are you right now? I mean, where are you at? Yeah.
It's basically following along with what you're doing. I mean, I wasn't able to get it, but.
So I would suggest you to do this. We actually have the exact working exploit in the slides, I think. That one should work. The only thing you need to replace there is the address, the return address on the stack. So as long as you replace that one, those first 2 bytes, so first the 4 bytes, then the other 4 bytes, if you replace that, it should work. Also, you need to disable ASLR first. Make that work first. If it works, then you just debug it to understand why it works. Then after that, you go back to starting from scratch to write your own script, own exploit. That might be easier. Okay, then how about Wei? You want to say anything, Wei, or are you still here? Okay, it's muted. Who else is here? I think that's. I think I called everyone there. Good. So how is the return to libc doing? Who are working on return to libc?
So far, I've collected all of my targets
Okay.
using RSH, so I think they should be aligned.
Okay.
I have some suspicions on where to put them,
Okay.
but I'm not concrete enough on understanding why to the point where I can make accurate predictions of where they're going to go versus how that's going to affect the runtime. Being that we only overwrote 1 byte to print secret, I'm seeing several more bytes that we would need to override if we were going to use the same kind of mechanism that we did for the last one, and I don't know if I have time to print all those.
Yeah. So also, Phil, you remember for return to libc, the argument is actually not direct, not not higher, only directly higher than the return address. It's actually, there is a 4 bytes there. There's a 4 bytes in the beating garbage. We use as a return address of the return the function. Yeah.
Yeah, I'll keep that in mind.
Yes.
That's where we put the graceful exit, right?
You can. You don't have to. Okay. Yes, you can. Yes.
That part's easier usually.
Yes. Well, technically, if your system executes, that graceful exit doesn't execute anyway, right?
Yeah, you would leave the shell and then get the clean exit
Exactly.
if that were the trick.
Yes. So what's the time right now? So right now it's not a 7 yet. Okay. For those who are still working on the first one, not to return to libc, can I help you anyhow? For example, if you have question for the last week's lecture, also let me know. I can explain to you. So next week, we are going to talk about something super exciting. Next week, we are talking about the ROP, return-oriented programming. So it's more like a generalized version of a return to libc. And it's, to me, ROP is kind of like one of the most important discoveries in security in the last, right now it's already 12 years. One of the most important discovery in security. And also, what else? If you think about the last 2 decades of security, you can think several major events, I would say, right? One is Bitcoin. Bitcoin is so important. Blockchain is so important. It influences not only security, it influences the financial world. So Bitcoin definitely one of those. Then the next thing I would think is probably ROP. I think ROP is that important. So next week we were starting looking at ROP. Very exciting topic. Can do a lot of ROP is so crazy. Like one of the energy people use, I like it really much. Is ROP is kind of like how you do Legos. So when you get a Lego box, you get an instruction, and you are supposed to do the Lego this way, and those Lego blocks are supposed to be assembled this way to do this. However, if someone give you a totally different instruction with the same Lego blocks, you can do something totally different. And the problem with software is before ROP, people didn't realize the binary, the software are actually just Lego blocks. Okay. They never realized that you can reassemble those binaries, those bytes together and make it to do something it was not intended to do at all. People didn't realize they're just Lego blocks, and then you can build whatever you want to build. So that's why ROP is very exciting. And one way to stop ROP is something called control flow integrity. We will discuss that as well, but it's a very heavy, computationally expensive approach, but it can stop ROP. Let me share my screen here a little bit. I think we have a little bit more to discuss. So that's basically about the format string vulnerability. And with format string vulnerability, you can have the ability to write arbitrary value to arbitrary address. So it's super powerful, and sometimes you can also have the ability to read arbitrary address, arbitrary value, and arbitrary address. Super powerful. So there are so many things we can override. So today we only override a local variable, a global variable, a return address on the stack. There are many other things you can override. For example, the GOT table, the PLT table, and it can make things much more generic. So far we haven't talked about those GOT and PLT tables. I'm not sure if we will. Right now, I don't have plan to do that. But in some real world CTFs, that's some the places you want to override. And also you can override any code pointers on the stack, on the heap, anywhere. So to stop this format string vulnerability, the compiler can do something. Actually, for example, the example IBEC showed there, if you compare a format string with a 3% there, then only give it 2 integers, then the GCC will actually tell you there could be a format string vulnerability. The GCC will tell you that. And also, if you compare things like the one we're using here, is we are directly using a user string as the format string, and you can say GCC will also warn you, right? GCC will say that format not a string literal, and there's no format argument. So the GCC will tell you this could be a problem, but the GCC doesn't stop you from doing this. Of course, there are other combination flags. You can treat all the warnings as errors, then GCC will stop compiling. But that is basically, at this moment, what the compiler can do. Of course, this is a potential problem because you don't really know if that format string has those specifiers until runtime. So that's why CSE can give you a warning here. So that is one of the defense, at least the warning. Then, like everything else, address-based layout randomization makes hacking really difficult, and that's why so far almost all our attacks disable ASLR because it's very effective, and it's the problem with it is, like we said, it's right now all the system we are using for kernel, it only happens at boot time. For program, it only happens at load time. So it's not like you can randomize things frequently. That's one of the limitations of ASLR at this moment, but still it's quite helpful. So if we compare format string vulnerability with the buffer overflow we looked at before, the main difference is we say the buffer overflow we had before, we call it a sequential overflow. We overflow from the buffer to everything on the stack, higher address than it. So that's why we can put some stack cookies there to make sure the stack guard, the stack cookies, they're the same thing to prevent those kind of, to detect those kind of attack. However, with format string vulnerability, the stack cookies do not work anymore because you can accurately, precisely only overwrite 4 bytes of the return address. You can just jump over the cookies, so they don't work anymore. This is not related to the executable stack or non-executable stack because we already know how to do return to libc. So as long as you can control the code pointer, you don't have to put share code on the stack. Okay, very cool. I think that's what I have for today. So for one of the homework, you should keep working on return to libc on this one. And I will also upload the other homework maybe tomorrow. And for last week's homework, you still have, I think you still have a week or something, right? And also for this one, if you have any problem, just ping me. Cool. Any other questions? Everyone is good? Okay. See you guys next week. We are doing Roth. Okay, cool. Bye.
Good night, everybody.
Bye. Thank you.
Thank you, Professor.
Professor Zhao?
Yes.
I have a quick question about the midterm.
Sure.
So in my grading comments, you had commented question